That is for the practice purpose. It doesn't mean that they will come into the examination or not. Just for practice purpose only, because you were saying that we have to just take the practice questions, some more practice questions. So I just put it some practice questions. So these practice questions, we can't say that they are related to the examination only, but the syllabus is almost covered in that practice problems. So we will start. This is the context session number 10. And we have started the joint distribution in the last class. So when we are discussing the more than one random variable, then we will just go for the joint distribution. So in this one, we are discussing the three parts, that is the joint distribution and marginal distribution, dependence and independence of the random variables, expectation, mean and variance. You can say like this one, similar questions may expect, but it is may. If I found something different questions, then I can give from your syllabus only. Okay. So in this one, we are just doing the three parts, discrete bivariate, continuous bivariate, and the multivariate. So firstly, we will discuss the discrete bivariate random variables. So in this one, for two discrete random variables, x and y, we write the probability that x will take the value x and y will take the value y. So we can write it as a probability when x is equal to x and y is equal to y. So here we are talking about the intersection. So this probability density function joint, this is known as a joint density function. It is equal to the probability when x is equal to x and y is equal to small y. That and means what? We are taking an intersection. So this is known as the joint probability mass function. Or joint probability density function. So same type of question we have already done in the last class. I am just repeating this one. So we are rolling a two dice. And now we are just changing x with the number of first die and y with the value of second die. So we are just taking here x is varying from 1 to 6 here, and their density function is 1 by 36 for all x and for all y. That's we have done in the last class. Okay. So the joint probability table is given in this form for the discrete case. So this is the values of x, this is the values of y. So x is equal to 1, 2, 4, 5, 6. So when x is equal to 1, and y is equal to 1, then joint density function is 1 by 36 here. Okay, when both are 1. So that is the intersection. When x is equal to 1 and y is equal to 1, then the joint density function is 1 by 36 here. Okay, similarly we can say x is equal to 4 and y is equal to also 4, so or 5. So if x is equal to 4, so it is coming this, at y is equal to 5 is coming this, so it is the 1 by 36 here. So this is the way to see the table specifically, or to make a table for the joint distribution. Okay, now you can say these are the probabilities, so definitely they are greater than between 0 and 1 always, and summation for all values of x and for all values of y, it should be equal to 1, otherwise it is not a density function. Now we are changing this one, that x be the value on the first die and the t be the total on the both side. Same questions we have done earlier. I am just repeating it. Okay. So when x is equal to 1, 2, 3, 4, 5, 6. So this is the value of x. Now this is the value of t. So x is varying from 1 to 6, but t is varying from 2 to 12. Maximum value of x is t is equal to 12 and minimum is 2. Okay, because when x is equal to 1, then t is equal to 2, 3, 4, 5, 6, and 7, because it depends upon the y also. Y is equal to 1. So 1, 2, 3, 4, 5, 6. So then t is equal to x plus y. It is from 2 to 7 only. Similarly, when x is equal to 2, we are talking about the t is equal to what? It will start from 4, 5, 6, 7, 8, 9, 10, 11. Sorry. It's up to 8. So it will start from 3, 4, 5, 6, 7, 8, because it depends upon the y. Y is equal to 1, 2, 3, 4, 5, 6. Okay, so that's why we are just taking. So x is equal to 1. So this is the table up to 1, 2 to 7. When x is equal to 2, then it is equal to 2 to 8. Then when x is equal to 3, then it is equal to the 4 to 9. Otherwise, their values are 0. Okay, when x is equal to 6, so it will start from 7 and then up to the maximum value 12. Got it? Now we can find out the different type of probabilities also based on that event. So even we are saying here y minus x is greater than equal to 2. So here y is equal to 2. If we are talking about the 2, so that is the 1, 3, 1, 4, 1, 5, 1, 6. That is the y minus x is always coming greater than equal to 2. Similarly, 2, 4, 2, 5, 2, 6, 3, 5, 3, 6, 4, 6. Okay, so here we are just making a shaded area and these are the points here. So we just add them their density function. Then that will give the probability when x minus y is greater than equal to 2 here. So this is the complete sample space is provided because we are giving for all values of x and all values of possible values of y, and it is defined as a event. So from that subspace you can define the event. You can calculate the probabilities very easily. You know it how to do it. Okay. Any query till now? Any query till now? I'm not getting any response. Am I audible? Okay. So it means no query. So the next concept which is coming in the joint distribution is a marginal distribution. Marginal distribution means what? Here we are taking the two random variable, let us suppose x and y, okay, or x and t, two random variables we were talking about, okay, that is the bivariate, two dimensional. Now we are taking the projection of two dimensional into the one dimensional form. So it is a function of x on alone and it's a function of y alone. Similarly here x alone and t alone, because they are also be a random variable. X and y we also be a random variable, but then we just define in the ordered pair, then it will become a two-dimensional random variable. Okay, so two-dimensional random variable we can transform into the one-dimensional random variable, and whatever we have done in the chapter 4 and chapter 5 we can apply all the concept of that, and then we can find out the different type of probabilities. So that is the benefit in the joint, that we can just go for the projection also, and we can also find out the every information about the x alone, means there is no effect of y in that one. Similarly for y alone, then we are not having the any impact of x alone. Okay, so that is the two different random variables, and we are trying to find out first what is the pdf, what is the cdf, what is the mean, and so on, that you can apply in the chapter 3 and chapter 4. Now after that you can just say here that This is known as the projection from two-dimensional to the one-dimensional. Okay, so the marginal density function for x is given as summation for all y fxy here. So now this is a function of x alone, because y which is we are taking, that is the constant value we are consider here. That is coming in the summation, that y is varying from 1 to all possible values of y. We are accumulate or the effect of that y actually. So that's why we are taking the summation for. I think that students are not taking interest in that topic because it is not coming easy too, because no question is coming, everything is like no interaction. Even I am just asking that is it okay, any doubt, any query, then no reply at all. Okay, fine, thank you, thank you. Similarly, we can find out the marginal density function for the y here. So marginal density function, it means what? Summation for all x fxy, the joint density function. Okay, so it is a function of y alone. Function of y alone. It should be y. It should be y. It is a function of y alone. Because we are just accumulate all the effect of x on y. So we are just taking only the y concept here. Okay, so now they are having their individuality for x random variable, for y random variable. So they are maintaining their individuality, and then they are finding, okay, this is a function of x only, density function. Then you can find out the cumulative distribution function. Then you can find out the expectation, mean, or any type of probability related to that particular random variable. Okay, so it doesn't mean that always we have to include the other variable in the calculation. No, because we have already done it, the first calculation. Okay, so that is the concept of the marginal distribution. Now there are two different functions we have mentioned. So here we can say fxy, or f we can just write it as fxy. So this is the joint density function. Okay, and then when we are using the suffix fx and fy, these are the marginal density function for x and y respectively. Be careful about it. We are not using the same symbol. We have to make a change in that symbol. Make a change means what? We are using the subscript of x, subscript of y. If you are not using the subscript, means what? We are using the same function, and which is not correct. Okay, always the definition of this function is coming different. So in this one, how you can calculate the density function, marginal density function. So what we will do, fxx we are mentioning here, and we are taking the row wise addition. So 1 by 36 to up to here 6 by 36. Okay, similarly here 6 by 1 by 6 by 36. Similarly, we can find out the marginal density function of y. So what we will do, we will just what we will do, we will just add column wise. So y is equal to 1, so we are adding it, and 1 by 6 here, 2, that is 6 by 36, then 3, it is 6 by 36, that will become 1 by 36, 1 by 6 actually. Okay, so we can write here as like this, that x is equal to, x is what? 1, 2, 3, 4, 5, 6. So fxx is become here 1 by 6, 1 by 6, 1 by 6, 1 by 6, 1 by 6 here. Okay, so you have the, can you recall this one that which we have done in chapter 4? No response. Okay, so we are doing the same manner. Similarly, we can write the y value 1, 2, 3, 4, 5, 6, and their fy is what? 1 by 6, 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 and 1 by 6 here. Okay, it's not a Poisson distribution, it is a general distribution. The probability density function, that expectation, then variance. Okay, and here we are using the summation because most of the time we are using the discrete case here. Okay, now in this one the same thing. In this numerical, if you are finding the fx, the CDF. So CDF is what? If we are writing like this one CDF, so for x on alone, so we are just using this one density function. So you can see it is 0 when x is less than 1. Okay, when it is become 1, then it will become 1 by 6. So 1 by 6 is from 1 is less than equal to x is less than 2. When it is reaching to 2, so it will become 2 by 6. So 2 is less than x is less than 3, then 3 by 6, then 3 is less than equal to x is less than 4, 4 by 6, so 4 is less than equal to x is less than equal to 5, and then 5 by 6, then 5 is less than equal to x is less than equal to 6, and 1 when x is greater than equal to 6. This is the way to write the cumulative distribution function. Okay, Mahinder, Mr. Mahinder? Similarly, joint density function we are doing for the second example. So x we are taking here 1, 2, 3, 5 to row wise addition. 6 by 6 by 36 and so on. Now similarly for x is equal to t is equal to 2, 3 up to 12 here. So it is 1 by 36, 2 by 36, 3 by 36, 4 by 36, 5 by 36, 6 by 36. Okay, similarly 5 by 36, so we are just doing the column wise addition here. It is coming same actually. It is not same, it is coming same because when we are adding here all the values, so it is coming 1 by 6. When we are adding these values, it is 1 by 6. So it is coming same, it is not same. Always in all condition, it is not same. For example, you can see here in the fy, they are not coming same. So when we are adding it, they are coming same by chance only. Okay, now there are two random variables, so we can check they are dependent or not dependent. Okay, so we are just using here fxy is equal to the joint density distribution is equal to the product of marginal density function, then they are called independent, otherwise they are dependent here. Okay, so for this example you can see here, if we are talking about this part and this part, so it is 1 by 6 multiplied by 1 by 36. Okay, so what we are doing, we are just using here the f of x at 1 and f of t at 1. Okay, so this is 1 by 6 and this is 1 by 36, and when we are just multiplied it, so it is 1 by 6 multiplied by 36, which is not equal to 1 by 36 because it's a 1 by 36 joined, so they are not independent here. Okay, so they are not independent. Okay, so that is the concept we are using. Any counter example you can take, then they are independent. In the previous example you can see in this one, so you can say here, let us suppose I am taking here fx of 3. Fx of 3 is what, if we are just talking about, that is 1 by 6, and we are taking fy or 4. Fy or 4, this is also become like 1 by 6. Okay, now we are taking f of x is equal to 3 and y is equal to 4. So this is what, x is equal to 3 and y is equal to 4. It is coming, should be 1 by 36. And we know 1 by 6 multiplied by 1 by 6 is equal to 1 by 36. So they are independent. Are you getting my point here? The independence and non-independent. So they are independent. The first question which we are taking, because x and y, they are the number coming out on the above. Okay, then they are independent to each other. By experiment you can also visualize. But x is the number of value we are just taking, but t is the total. So if t is that, it depends upon the value of x also, because t is totaling, that is coming based on x and y here. Okay, we are not considering y here because we are considering t here. Okay, so x and y, x and t are not independent to each other. Why? Because if we are taking the experimental concept, so it means what, they are dependent to each other. Which explanation? You know the marginal density function? You can pick any 2 points. You can check every point actually, and that should be equal to the joint distribution corresponding. Okay, so first entry we are picking here, and first entry we are picking here, and then that is the first entry from this table. Any value you can pick. Okay, if they are they are equal, the multiplication of marginal density function is equal to the joint density function, then we can consider they are equal, they are independent. Okay, I already gave you this example here. Now next is show more example. We will do some more examples, then I will share at the time also that they are independent or dependent. Okay, so if they are independent, then it is okay. But if they are not independent, they are dependent to each other, then the concept is coming the conditional probability that you have done in the chapter 3. Do you remember chapter 3? We are just having the 2-3 events and we are just saying they are independent. So what the condition we are applying? They are known to be independent if and only if we call the chapter 3. Two random variables or two events, they are in A and B, and we can say they are independent if and only if x is equal to 0. I'm not getting the response from the chapter 3 actually. That is also part of EC2. Here we are using this EC2. So in that one, we are saying that two random variable, two random events are known to be a independent if their probability. So if you remember, we could define the probability of A intersection B is equal to probability of A multiplied by probability of B. So they are independent. If they are independent, then this condition should satisfy. Okay. So if they are conditional probability, so if you remember, we are just doing the conditional probability also. So in the conditional probability, if you remember, the probability of A given B is equal to probability of A intersection B upon probability of B, provided the denominator is not equal to 0. Otherwise it will become infinite. Okay, same concept we are applying here. The conditional density function can be written as joint density function divided by the marginal density function, provided that denominator is not equal to 0. Okay, so that is considered as probability of x is equal to x given that y is equal to y. So we fix some value of y and then we can change the impact of, we are finding the impact of x. Okay. Just give me 1 minute. I am just going to drink water. So in example 2, because in example 1, the two random variable x and y we are talking about, they are independent. So we can't find out the conditional probability. Okay. So in example 2, we are just taking a, they are dependent to each other. Then we are finding what is the total value of 4 given that the value on the first die is 3. So we have to calculate the f of total value t and given x is equal to 3. So here we are just finding t is equal to 4. Okay, so how you can do it? So t is equal to 4 and x is equal to 3. So t is equal to 4 is this and x is equal to 3 is this. So it is 1 by 36. So this is the joint density function 1 by 36 upon the density function for x is equal to 3 is what? 1 by 6. So 1 by 6. So it is become here 6 by 36. So it is why 1 by 6. Are you getting my point here? This is the joint density function. This one 1 by 36. At the same point, x is equal to 3 and t is equal to 4. Okay, now we are using the marginal density function for x is equal to 3 because that is coming in the denominator. So that is by 6 by 36. So it is 1 by 6. Got it? Next question. Value on the first die is 2. Given that, now they are just changing the concept that x is equal to 2. Given that total value is equal to 8 and x is equal to 2 here. Okay, so what you will do here in this table, x is equal to 2 and t is equal to 8. So here this one. So this 1 by 36. Okay, so it is 1 by 36 divided by. Now we are taking the density function for t because given that it is t is equal to 8. So t is equal to 8. It is the density function is 5 by 36. Okay, so when we are just taking this will become 1 by 5. Okay, so this is the method that we can just use the joint table and then the marginal table to find out the conditional values. Are you getting my point? Why we are taking 5 by 36? That is the marginal density function for t. Okay, Mr. Vinkata, 5 by 36 is marginal t at t is equal to 8 is by 5 by 36. So that is coming in the denominator. Because what we are taking, we have to find out x given t. So it is the fx comma t upon f of t. Either table is given or you have to calculate the table. Because in that one experiment are given, based on that experiment you have to create the table. Otherwise table is given already. Yes, table is standard. Depend upon the question to question. Okay, now we can say if two random variables are independent, the conditional probability is become here the same probability fxx. The density function is same. How you can do it? Fx given y is equal to what? Fxy upon fxx. Ffy. Okay. Now you know that density function, if this is the independent, then we can write it as fxx into fy of y. And in the denominator we have already have fy of y. So that's why we can say it is equal to the this. What I have to repeat, Mr. Nilesh? So if they are independent, then there is no meaning of the conditional probability, that is coming the same as the simple marginal probability. If they are independent, if they are dependent, then we can't say anything. Last table, this table. This table we have made already. We have made it in the event that rolling it 2 dice. X is the number on the first die and t is the total number. है ना? So that we have done earlier. Then we have done earlier this joint table. Then we have done the earlier that about the marginal row wise addition and column wise addition, that is known as the marginal density function for x and y respectively. Okay. And from that, we can also find out the conditional probability. Now come to the expectation. You know the concept of the expectation we have done in the chapter 3, chapter 4. So same concept, only the thing is what we have to add for all sample space. And as in the sample space, there are two random variables. So for all x and for all y, we have to add it. So we have to check all the values, means for all values of x required and for all values of y required. So we have to do, then we can identify that what is the expectation. Okay, so expectation, mean and covariance, which we are taking here. So expectation of any function hxy can be written as summation for all x, summation or all y, hxy multiplied by its density function. The same question you have done. If we are finding expectation of x, if we are just talking about the hx, so what you will do? You're taking summation for all x, hx multiplied by density function. Same here we are doing. Okay, so in this one, the only thing is, because there is not only one x, there is two random variables. So we have to take summation for all x, summation of for all y. Okay, so that's why we are taking a mu x. We have two random variables, so we have to define whose mean we are trying to find out, mu x and mu y. Okay, so expected value of x is equal to summation for all x, summation of all y, x multiplied by fxy. So we are taking the weightage whose expectation is we are trying to find out. Okay. That can, oh sorry, that can be also can be defined by this one, because it's a function of x alone, so we can use the marginal density function also. Okay, that we have done here. So for x function only, we can use the marginal density function. We multiplied it by x and taking the summation for all values of x. If you have already calculated by x, then it is okay. Otherwise, you have to use that concept also. That is very easy actually. Okay, similarly, we can find out the mu y. Mu y is what? Summation for all x, for all y. We are taking mu y because it is expected value of y. So y multiplied by density function, joint density function. Okay, and that we can also find out summation for all y, y into fy of y, that marginal density function. So we can use by both method to calculate the expectation of x and expectation of y. But if we are finding the expectation of xy, so that is not possible by using marginal. With that we can find out by using the joint only. So as I told you, we are trying to find out expected value of xy. So what you will do, we are taking for all values of x, for all values of y, xy multiplied by joint density function. Okay, in this case we can't apply the marginal density function because both the random variables are coming into the picture here. Got it? Now the next term is coming, this after expectation we have done the covariance, variance. So same here we are using the covariance. So covariance is the expectation of x minus mu x, y minus mu y, and that is we can find out by the formula, direct formula, expected value of xy minus expected value of x and expected value of y. Okay, any query till now? I am going very slow. So Variance of x, if you just remember that we have done x minus mu x up whole square now. So that we are doing. Now we are just doing here, instead of that whole square, we are using the covariance of x comma y. There are two random variables, expected value of x minus mu x and y minus mu y. Okay. And when we are open it, I'm not getting your three unknowns. X and y are random variables, so it's any function of x and y is known as the random variable again, which is known as h. Its function value is given in your question. Example, I'm not doing that example. I believe that you can do it. Random experiment, toss of two fair coin. X denote the number of heads and Y denote the number of tails. Okay. Find out the joint density function. Find out the cumulative distribution function. Find out the marginal density function. Then after marginal, we can check whether X and Y are independent or not. If they are independent, then it's okay. If they are dependent to each other, then find out the covariance of xy, because if they are independent, then the covariance always coming 0 here. Okay, so we are just saying x is the number of heads, two fair coins, and y is the number of tails. So you can say here, like in this one, the solution, x is 0 1 2, number of heads in the two coin, number of tails in the two coins, so 0 1 2 here. Okay, now density function is what? It is coming here 1 by 4, when 1 is x is 0 and y is equal to 2. And similarly here, we generate this joint table here by taking the events basically. Okay, so here it is 1 by 2 and it is 1 by 4 here. Clear? Oh. Okay, now second we have to find out the cumulative distribution function. So in the cumulative distribution function, what we are doing here, that we can just find out the probability when x is less than equal to 2, 1, and y is also less than 1. So that is the CDF. So what we are doing, x is less than equal to 1, so we are just saying x is 0 and 1, and y is also less than equal to 1. So we have to add these two parts. So it is coming half. Okay, so it is 0 0 1 by 4, 0 1 by 4, 1 by 2, and then we are adding, so it is become 3 by 4. When we are taking 1 by 4, 3 by 4 coming from this, and it is 1. Now marginal you can see we are adding row wise, so 1 by 4, 1 by 2, 1 by 4. So it is like this. Column wise we are saying 1 by 4, 1 by 2, 1 by 4. Correct. Bilkul correct, Mr. Sanjay. Here I am just mentioning less than 1 and less than 1. So if there is no need to add it 1 here. So it is this one. Only the value is coming 0. We are not, we don't, not supposed to consider 1. Because is it directly less than 1, not equal to 1. Which table is formed? Is this table? The first table. Okay. So first table is what? You can just go back. What is the question? Question is the X denote the number of heads and Y is number of tails. Okay, so X can vary twice up. You are just okay. You are just twice. You are flipping a coin. Okay, so now X is what number of heads. So X when you are just taking a sample space, how it is possible? Okay, so it is what is the two times head is coming, head and tail, then tail and head, and then tail and tail. This is the complete sample space. Clear? Now X is the number of head. X is the number of head. It may be 0, it may be 1, it may be 2. Okay, number of head. Now density function for X is equal to 0, 1 and 2. Similarly, Y is also 0, 1 and 2 number of tail. Now you can see here head and head is coming both. Okay, one time. So head is coming here. Okay, so from that, when X is equal to 0, 1, 2, you can see here X is equal to 0, then it is coming what? You can't find out the thing. When X is equal to 0, okay, you can just check like this one. When X is equal to 0, I make it like this one, 1 and 2, and then Y is also become 1, 0, 1 and 2, Y. Okay, now X is equal to 0 and Y is equal to 0 means no head, no tail. Is it possible? No possible. So that's why the probability is 0. No head, no tail. Okay, when X is no head, out of two toys there is no head, so one tail is possible? No, because at a time both should be tail. So both should be tail means what? That is the TT, and that what is the probability of coming TT? It is 1 by 4 here. Got it? Similarly, when X is equal to 1 and Y is no tail, X is equal to 1 head, but Y, what is the other one? So that is again 0 here. Okay, but here when X is equal to 1 and Y is equal to 1, that is one head and one tail. So there are two options. So that's why it is 2 by 4 here. Again, if X is equal to 1 and Y is equal to 2, that is also not possible at all. Similarly, when X is equal to 2, then we are getting here two heads. So it means it is 1 by 4 here. Clear? But when X is equal to 2, then Y is equal to 1, not possible. X is equal to 2 and Y is equal to 2 is not possible here. This is the way to make the table by consider the event. What type of experiment we are doing here. Got it, Mr. Dhamutaran? 2 by 4 is 1 by 2 only. Yes, that is we have taken two cases, na? Head and tail or tail and head. Now covariance and independence. So covariance, as I told you, so covariance is the measure of joint variability of two random variable. Means what? If X is 0, X is 0 means there is no head. So what is the possibility? If there is no head, so it means both cases are coming tail. So that's why it is 0 and it is 0 and that is tail. है ना? When it is become one tail, so there should be one head. If one head, then one should be tail. At a time we can't say that after that one is tail, but other is what? We don't know. Okay. So there covariance basically which is used to find out the relationship between x and y, is they linearly related or not. Okay, so the concept is linear. It is very important. I'm just showing you here. Just wait. Just wait, covariance. Okay. So if x and y are independent, then we can say the covariance is coming 0 here. Means they are not dependent to each other. So that means they don't have any relationship between them. That's why covariance is equal to 0. But if covariance is equal to 0, doesn't mean that x and y are independent. Okay, because that is a simple calculation. By chance this calculation is coming 0, so it doesn't mean that x and y are independent. So it is only a sufficient condition, not the necessary condition. Okay. And the second thing is what? That zero covariance means no linear relationship, because we covariance we are saying for the linear relationship. So it may connected to each other, as we are saying they are not independent. They may be dependent, but they don't have the relationship which is not linear. Which is not linear means it may have a non-linearity in their relationship. Okay, so it does not imply that they are unrelated. They are maybe related, maybe, we don't know. If x and y are covariance is 0, so we can't conclude that they are dependent or not dependent. But definitely if they are independent, the covariance is coming always be 0 here. Mutually exclusive, no, we are not using this concept as a mutually exclusive here. That is different concept. Here this is different concept. That is the independence, not a mutually exclusive. Okay, so now covariance formula, you are saying now how covariance is coming here minus half. So I'm just telling you the covariance formula we have done earlier. Covariance of xy is expected value of xy minus expected value into expected value of y. You can calculate expected value of x, you can calculate expected value of y, you can calculate the expected value of xy. So how you can calculate the expected value of xy? Can you tell me in this one? So this is the joint table. So we can say here xy. So it is what? Summation for all x, for all y. It is x into y into fxy. है ना? ठीक है. So first we start from x is equal to 0. So x is equal to 0, y is equal to 0, and fxy is equal to 0. Plus x is equal to 0, y is equal to 1. So fxy is equal to 0. Plus x is equal to 0, y is equal to 2. Then fxy is 1 by 4 and so on. है ना? So we are getting only the concept when it is 1 multiplied by 1 multiplied by 1 by 2. This part, because this is multiplied by 0, this is multiplied by 0. All other are 0. That's why expected value of xy is coming here 1 by 2. Now we can say expected value of x is what? Expected value is what? 0 multiplied by 1 by 4 plus 1 multiplied by 1 by 2 plus 2 multiplied by 1 by 4. So it is become half and half. So it is 1. Similarly, expected value of y. So it is 1. So expected value of xy minus expected value of x into expected value of y. And a covariance formula is this. So here expected value of xy we have already calculated. This is half. Half minus 1 multiplied by 1. So it is half minus 1. So it is minus half. That's why the covariance is coming minus half. Are you getting my point here? I have shown all the calculation. If you want to do it your own, so I am taking a break and you can just take it. Do it your own and you can just. I am just open it. You can see. You can see. Okay, 10 minutes break, please. Okay, thank you. You can see here and you can do your calculation. Then you can understand what we are trying to do here. Okay, break. You can see the calculation I have done on the calculation, Mr. Mahinder Singh Rawat, that expected value of xy is equal to half. For all values of x, for all values of y. Got it? Am I audible? Am I audible? Yes, Mr. Kadam. Thank you. So I just gave you one example. Okay, thank you. I'm just giving you the one example here when covariance is coming 0, but they are not independent to each other. Okay. So firstly, we are just checking they are independent or not. So we are just taking here f of xy, f of x is equal to 0 and y is equal to 0. So this is a joint density function. So it, oh, sorry, they are not 0 and 0. So x is equal to 1 and y is equal to -2. Okay. So this value is 0. Okay. But when we are taking fx at x is equal to 1, so it is coming here 1 by 2. So it is equal to 1 by 2. And we are taking fy at y is equal to -2. So this is 1 by 4. So it is 1 by 4. So we can say 1 by 2 multiplied by 1 by 4 is not equal to 0. So they are not independent. Correct? First, we check that they are independent or not. Got it? Now we are calculating the thing that expected value of xy. Expected value of xy, it is what? Summation for all x, summation for all y, xy, fxy. Correct? We are doing the same thing. Now we are doing for all x. So you can see here x is equal to 1, y is equal to -2, and it fxy is 0. Plus 1 multiplied by -1 multiplied by 1 by 4 plus 1 multiplied by 1 multiplied by 1 by 4 plus 1 multiplied by 2 multiplied by 0. Correct? This is for all x. Now we are just doing for y. So 4 multiplied by -2 multiplied by 1 by 4 plus 4 multiplied by 0 multiplied by -1 plus 4 multiplied by 1 multiplied by 0 plus 4 multiplied by 2 multiplied by 1 by 4. Correct? So this is become 0, this is become 0, this is become 0, this is become 0. So now we are getting here, this is -1 by 4. Correct? This is 1 by 4 plus 1 by 4. Okay? This we are getting here -8 by 4. Correct? And this is also plus 8 by 4. So they are cancel out, and here expected value of xy is become 0. Correct? Now expected value of x we are calculating. So expected value of x is what? summation x fx, है ना? So we can say x is what? 1 multiplied by 1 by 2 plus 4 multiplied by 1 by 2. So that will become here 1 by 2 plus 2. So 5 by 2. Okay. Now expected value of y is what? Minus 2 multiplied by 1 by 4 plus minus 1 multiplied by 1 by 4 plus 1 multiplied by 1 by 4 plus 2 multiplied by 1 by 4. Correct? So it will become here minus 2 by 4 minus 1 by 4 plus 1 by 4 plus 2 by 4. So this answer is coming 0. Now expected covariance is what? The formula is what? Expected value of xy minus expected value of x multiplied by expected value of y. This is 0 minus expected value of x is what? 5 by 2 multiplied by 0. So this is 0. So here you can see the covariance is coming 0 where they are not independent. We have already checked it here that they are not independent, but covariance is coming 0. Okay, so if they are they are independent, then covariance is 0. Independent, then definitely covariance is equal to 0. But if covariance is equal to 0, we can't conclude that they are independent. Are you getting my point? One example I have given. Is it clear to all of you? So in this example, which we have done the calculation of finding expected value of x. We are calculating the covariance of x, expected value of xy. So all calculations which we are doing here, that is a part of the syllabus actually, which we required, which we are doing here. Okay. Same example we are doing here. This is also one example. Okay. Just do it your own. Now one example which is your question of your textbook. The two random variables are independent and each has a binomial distribution with success probabilities 0.7 and 4 trials. Okay, 0.7 and 4 trials. Find the joint probability distribution. How you can find out the joint probability distribution in that case? Because they are independent. Okay, so you can see here the 4 trials. So there are variables. X is what? 0, 1, 2, 3, 4. So you can find out their density function fxx. Marginal density function you can calculate. N is 4 and p is equal to 0.7. So from the table you can get the values here. है ना? Or you can calculate it by using the NCX, p to the power x, q to the power, or q instead of q we are using 1 minus p to the power n minus x. है ना? You are putting x is equal to 0, 1, 2, 3, 4 and so on. And then similarly you can find out y. Y is also 1, 0, 1, 2, 3, 4. And again each has a same. So there is the same values are coming. So whatever the value is coming here, you can just multiply it. That is what? F of xy. Okay. So I will show you the table. Okay. Solution is not there. So you just calculate your own and you can find out the answer. Clear? So I already mentioned here that it is a binomial distribution. So you have find out the x, y values here and you just multiply it this one. Then let us suppose here it is coming a. This is coming A1, A2, A3, A4, A5. And let us suppose this is B1, B2, B3, B4, B5. These values you can calculate. I am not doing it. It's up to you because it follows the binomial distribution which you have done. So now the joint density function is what? X is varying from 0, 1, 2, 3, 4. Okay. Y is also varying from 0, 1, 2, 3, 4. This is Y. So this value is what? A1, B1. This is value is what? A1, B2. This value is what? A1, B3, A1, B4, A1, B5. Okay. Similarly here, this is A2 with B1, A2, B2, A2, B3, A2, B4, A2, B5. You just calculate all the things here. So you have to make this table. That is the joint table. Find the probability the first random variable is greater than the second. First random variable is greater than second. Okay, so how we can say the first random variable is x, second random variable is y. So we are just saying here that it is 1 0. That will start from here. This one, 2 is going like this one, then this one, this one. Okay, and we are not including this 4 here and this part, bus only this. So these entries we have to add it. So for example, I am just giving you here the entries are A2B1 plus A3B1 plus A3B2 plus A4B1 plus A4B. First is greater than, yes, B2 plus A4B3 plus A5B1 plus A5B2 plus A5B3 plus A5B4. These entries you have to add. Okay. Now it's up to you how you can do it. Just consider as a practice problem. Okay. I already gave you the hint. Please do it your own. Any doubt, you can drop a one mail here. Now continuous. So that is related to the chapter 5, which you have done. Yes. Mr. Pankaj, why you are surprised? So in the chapter 5, in chapter 4, you have done the discrete random variable. So till now we have done the discrete joint distribution. Okay. And in the continuous case, that is chapter 5, we have done now when we are using the continuous random variable. So what is the difference in the discrete and continuous? In the discrete case, we are using the summation, and in the continuous case, we are using the integration. So all concept of the joint distribution, whatever we have done till now, the same, only summation is replaced by the integration sign. Okay, so for two continuous random variable x and y, we call the ordered pair x and y a two-dimensional or bivariate continuous random variable, and in that one a function fxy such that greater than equal to 0, and that integration is coming here for all r fxy dx dy, then this is known as the, yes, before joint distribution, before 5.10, section 5.10, that will come. Okay, and we can just say that integration for all x is equal to minus infinity to infinity, and y is equal to also minus infinity to infinity, fxy dx dy is equal to 1. Okay, so then it is known as the joint probability density function for x and y here. Okay, and this is the domain because it belongs to R, so we are integrating over this domain R here. So whatever we have done in the discrete case, we are taking the summation. Here we are taking the integration because all values are real values, they are continuous values, so we can't take the summation, we have to take the integration. That you know very well. Okay, we have done this part in the chapter 5 basically. Okay, so how to find out the CDF? CDF is what? X is equal to minus infinity to a small x, y is equal to minus infinity to y, and then we are using fxy dx dy. So this is what? This is basically a double integration which we are using here to find out the CDF, because there are two variables. So in the joint distribution discrete case we are using the 2 times summation. Here we are taking the 2 time integration, double integration, which is known. Okay, now marginal density function, that we are just integrating the joint density function with respect to y is equal to minus infinity to infinity. So this is function of x alone. Similarly, when we are just integrating joint density function with respect to x, so that will become here marginal density function of y. The same thing which we have done earlier, only we are replacing summation with the sign of integration. Correct? X and y are called to be independent. You know, if there are marginal, product of marginal is equal to the joint. That is the same which we have already done. That product of the marginal is equal to the equal to the joint distribution. Then we can say for all values of x and y, then it is known as an independent. Otherwise, it is not independent here. Expectation, the same thing as we have done. So expected value of hxy is what? X is equal to minus infinity to infinity, y is equal to minus infinity to infinity, hxy multiplied by fxy, and we are just doing the 2 times integration here. So when we are taking the mu x only, in that is what? Expected value of x alone. So we are taking here x is equal to minus infinity to infinity x and marginal density function for x. That we can also do it here. Integration for x is equal to minus infinity to infinity, y is equal to minus infinity to infinity x, and joint density function with dx dy. Okay, dx dy. Similarly, we can say mu y. For marginal we can use here. So if y is equal to minus infinity to infinity, y of fy dy, we integrated with respect to y, and we can also use the joint. So what we are doing, x is equal to minus infinity to infinity, y is equal to minus infinity to infinity y, and then we are using the joint density function dx dy. Correct? Similarly, we can find out the expected value of xy. How you can do it? X is equal to minus infinity to infinity, y is equal to minus infinity to infinity multiplied by xy, and the joint density function, and dx and dy. Okay, so we can find out the expected value of xy, we can find out the expected value of x, expected value of y, then we can calculate the covariance of xy. Okay, so whatever we have done earlier, we are just extending, or we are just elaborate in the form of continuous random variable, which you have already done. That's why I'm just doing fast here, because you have done already the chapter 4 and chapter 5. Okay, now one example we are taking here. A bank operates both a drive up facility and a walk up window. Okay, there are two things. On a randomly selected day, X is the proportion of time that the drive-up facility is in use. Okay, means what? At least one customer is being served or waiting to be served. And Y is the proportion of the time that walk-up window is in use. Okay, there are two type of facilities. The set of possible values of x by is a rectangle D when x is equal to between 0 and 1 and y is also between 0 and 1. Okay, suppose the joint density function is given by this formula. Calculate the probability that neither facility is busy more than 1/4 of the time. Okay, so firstly, what you can find out here, density function is given. You can calculate any type of probability, you can calculate any type of expectation, marginal density function, everything here. So they are not busy till the 1/4 of the time. So that's why x is from 0 to 1/4 and y, oh sorry, y is also 0, 1 to 4. So what we are doing, x is equal to 0 to 1/4, y is equal to 0 to 1/4 and fxy. So I am just doing it here. X is equal to 0 to 1/4, y is equal to 0 to 1/4, and the density function 6/5 x plus y square dy dx. Okay, now we can just state what we are, just separate them. So that is equal to 0 to 1/4, 0 to 1/4, 6/5 x dy dx plus 0 to 1/4, 0 to 1/4, 6/5 y square dy dx. Correct? For the simplification. Now what we are doing, we can integrate it. So we are just integrating with respect to y first. So 6/5 is integration, x is equal to 0 to 1/5, 4, 6/5 x. So x, and we are integrating with respect to y. है ना? And this is also 0 to 1/4, and dx is remaining here, plus y, x is equal to 0 to 1/4, 6/5, and that is what, y square. So x y square and integration 0 to 1/4, and we have to just do it with y, with respect to y we are doing na, so it is coming, just a minute, y cube by 3 and dx. Okay, so 6/5, y's limit is what, 1/4. So multiplied by 1/4, and x is equal to 0 to 1/4 x dx. Okay, plus that will become here 6/5, and it is become multiplied by 3 and y cube 1/64, है ना? This one. And here it will become integrations, x is equal to 0 to 1/4, 1 into dx. All things are constant, that is we are taking outside. Now it will become like this one, integration 2/2 x square by 2, 0 to 1/4, plus okay, and 1 means what, x, and 0 to 1/4. Now we just applied 6/20 and multiplied by 2, and here it will become 1 by, okay, plus and that will become here 1/4. So you just solve it, answer, and answer is coming 7/640 and 0.01. Question is this. So question is, calculate the neither facility is busy more than 1/4 of the time. XY gone. XY gone, definitely we have to write the limits also. 1/4 of the time, that's why 0 to 1/4 and 0 to 1/4. We are integrating and we are getting the answer. Okay, I showed you the calculation also, the integration also. I believe that you have to do it. Now we have to find out the marginal of x, which gives the probability distribution of busy time for the driver facility without reference of the walk-up window. So it is what? That x is become fxx, that is mine x is equal to y is equal to minus infinity to infinity, but y varies from 0 to 1, otherwise it is 0. So that is, we are saying 6 by 5. I will just do it here. Fx x is equal to y is equal to 0 to 1. Why we are taking 0 to 1? Because otherwise it is 0. So that's why all terms are become 0. 6 by 5 x plus y square dy dx. Okay, or not dy dx. Okay, now we can just differentiate it, integrate it. So 6 by 5 xy plus y cube by 3, 0 to 1. So 6 by 5 y is, so it will become x plus 1 by 3. So it will become 6 by 5 x plus 2 by 5. In the range of x is 0 is less than x is less than equal to 1. ठीक है ना? Similarly, fy of y we are calculating. Okay, same process. Y, so we are integrating x is equal to 0 to 1, 6 by 5 x plus y square dx. Okay, so 6 by 5 x square by 2 plus xy square, and the range is 0 to 1. So 6 by 5, that is 1 by 2 plus y square. So we can say 6 by 5 y square plus 3 by 5. Okay, in the range of y is less than equal to 1 here. Is it clear to all of you? Now, if we are calculating the probability when y is less than equal to 1 by 4 to 3 by 4, so what density function we are using? We are using the, yes, this question is the related to the previous question only. We are finding, first is the finding different probabilities, second is the find out the marginal density function basically. Okay, same question. And in this one, we are finding the probability when y is between 1 by 4 to 3 by 4. So same, we are using which the marginal density function here. So what you will do here, probability of 1 by 4 is less than y is less than 3 by 4 is equal to integration y is equal to 1 by 4 to 3 by 4 fy of y. So it is 6 by 5 y square plus 3 by 5 dy. Now you can do it, I believe. So we are just saying here 6 by 5 y cube by 3, and the limits are 1 by 4 to 3 by 4 plus 3 by 5, and that will become y only 1 by 4 to 3 by 4. When you are just calculating these values, you will get the answer 0.4625. Only the calculation I am leaving on you. All hint I am giving here. Please try to do it your own, because it's a mathematical subjects, and without doing only the seeing the video and only seeing the slides, it's not possible to do it. Okay, is it clear to all of you? Now the next part is what? The find out the conditional PDF of y given that x is equal to 0.8. So how to find out the conditional of y? given x is equal to 0.8. So what is we are taking? The x of y upon f of x. Okay. So f of xy is what? 6 by 5 x plus y square, where f of x we have taken as क्या था? We just f of x, this one है ना, 6 by 5x plus 2 by 5. Correct. Now we are putting x is equal to 0.8. So it is 6 by 5, 0.8 plus y square upon 6 by 5 into 0.8 plus 2 by 5. So we are calculating it here. Then answer is coming 1 by 34, 1 by 34 of 24 plus 30y square. And y is between 0 and 1. Clear? So that is the conditional probability. So it is simple formula based, and this part is coming in the EC3, that is the open book examination. So there is no need to remember the formulas. So here we are doing the three type of distributions. First is the joint distribution, second is the marginal distribution, third we have done the conditional distribution. है ना? Conditional density function we are finding, which are based on the joint and the marginal here. So three type of density function we have done here. Okay. Now based on this conditional density function, we can calculate the probability. So probability, the walk-up facility is busy at most half. At most half means 0 to half. Okay. Minus infinity to half here. The time given that x is equal to 0.8. Okay. So the time given for that is 0.8 means what? It is a conditional density function. So we have to find out probability when y is less than equal to 0.5, when n x is equal to 0.8. है ना? So we are using the same density function which we calculated here, the conditional, because what, the probability we are finding the conditional probability, so that's why we are using the conditional density function. Correct. So if we are calculating the simple joint probability, so we are using joint density function. If we are calculating the marginal probability for x or for y, only for x, only for y, so we are using the marginal density function for x and y respectively, whatever it is required. And if we find out the conditional probability, so that's why we are using the conditional density function here. That is the use. Got it? Any query till now? So some examples I am giving you here for your practice purpose. As I told you in the last class also, I gave so many examples. So you will just try to do it. So 2-3 examples. One example solution is also given to you. Okay. For the joint distribution. Now please try to do it your own here. Okay. Some more important results on expectation, that expectation of ax plus b is equal to a expectation of x plus b. Variance of ax plus b is equal to a square variance of x. Okay. Simple. A expected value of ax plus by, that is the expected. These two you have already done in chapter 3 and chapter 4, but in the chapter 5 we are chapter 4 and chapter 5, now we are doing expected value of ax plus by. So a expected value of x plus b expected value of y. Similarly, covariance of ax plus b, cx plus cy plus d can be written as ac. A and C is coming from that, and covariance of XY. So there is no need to calculate in a complex manner. Directly we can use it. Okay. If X and Y are independent, then we can write the expectation in that manner. That is, expected value of XY can be written as expected value of X multiplied by expected value of Y. Okay. If they are, X and Y are independent. So these are the some properties which we can use to calculate the different type of expectation, variance, covariance, and so on. So they are not complicated. They look like a complicated question, but you can use these property to make it very simple. Okay. So next topic is moment generating function. I am not doing this one because time is almost over. So I'm stop here. So today we have done the joint distribution. I am just again recall it. Joint distribution. In this one we are using the discrete case. We have done the continuous case and we have done the multivariate. Okay. So in the next class we will start the moment generating function here. Mr. Rohit, the last moment preparation tips is that I have uploaded the practice problems. So firstly, you just go through all the videos, try to understand the concepts and try to solve these practice problems. Okay, fine, fine. Mr. Lokesh, you can see I am just doing the here the practice, the important topics only. Whatever we are discussing here, all are important because in the examination we are giving the question of on all the topics. You know, I'm trying to make it easier, but easy word is very vague actually. It may be easy for you, but it may be tough for any other students. है ना? So that's why I can't say that okay it is a easy. According to me, I will try to make it very easy. I already uploaded the practice problem. So if you don't have so much time, that's why I just put the practice problem. At least these are the minimum requirement that you have to solve these questions by your own. Okay, again don't take it from the other because this is not evaluative practice problem. So you just do it your own, try to find out the answer, do it by your hand so that you can do it the questions in the examination also. That will make you practice actually. Okay, so don't copy from the others, don't see the questions. Next quiz will be come in the after some time only. You can see the notice. That is notice only. It will be on eLearn portal. EC2 syllabus, I already told you EC2 syllabus. Before joint distribution, this is the EC2 syllabus. Before 5.10. I will try to make it easier, but please do the practice, then only you can solve it the easier question also. Nothing is easy in the mathematics and nothing is hard in the mathematics. Okay, mathematics is a very scoring subject, and this subject, this course which we are doing, it's very scoring, very easy calculation. We are not doing so much hard type of a core type of mathematics here. Concept wise mathematics we are doing here. So do it your own and try to understand the concept, which formula is applicable. As I told you, summary I have already given to you, that you have to identify, okay, this problem is of which distribution, which formulas is applicable, you can do it. Yes, in practice paper I have given the questions from chapter 3 to chapter 5, and chapter 5 is not completed, means we have not included the joint distribution as well. Chapter 2 is there. Chapter 2 is very small part is given, where which you can do it your own. More focus on the chapter 3 and chapter 4 and chapter 5. Okay, so have a good day. Thank you so much.